In this video, we'll talk about if we are going to use approximations, whether they're Riemann sum approximations left or right, whether they're midpoint approximations, whether they're trapezoidal approximations. We know that it's not the exact value, it's not the exact answer, but it at least gives us an idea of what that value could be. Important in that is understanding whether the estimate that I have is too low, is it an underestimate, or is the estimate that I have too high, is it an overestimate? And for that, we can think about how to analyze whether or not we have one or the other. And so the tables that you're given here are really just telling you how you can tell whether a function, whether the approximation that you're getting, if it's left or a right rectangle, is it going to be increasing or decrease? Is it going to be an over approximation or an under approximation? And if I just draw a picture here to kind of help us visualize, and so let's say I have a curve that's increasing. So that would be this situation and this situation, right? And if I were to start drawing left-sided rectangles say, hey, start at the first left side endpoint and go over, go over, go over, but the height of the curve is determining the height of the rectangle, right? But I'm starting from the left side. And as you can see, all of these rectangles are under the function. So because the function is increasing, I know that my left-sided Riemann rectangle is an underestimate. Now that's different than if I were to do a right rectangle. If I did this one, then the right rectangle would come up here and it would go backwards. Oh, that's over, and you can see that that's definitely going to be an overestimate. Well, same or similar behavior if the function is decreasing. Now when I look at the left side, I start from the left side and I go over, and you can definitely see that now my rectangles that go above the curve are coming from my left side, which is what this is saying, and vice versa with the other part. Now, when I'm looking at midpoint and trapezoid approximations, oh, by the way, when I use the explanation that f of x is increasing, that's the explanation why I have either an under and over estimate. I can also think about what we've talked about in the previous unit, which is I know that f of x is increasing if f prime of x is positive, really greater than or equal to 0. But if it's positive, then I know that it's increasing, and therefore I would have that analysis of over or under estimate. When I look at midpoint and trapezoid approximations, it's not as easy to use the increasing and decreasing. So we use the second derivative, and the second derivative, if you recall, is really about concavity. And so let's say that I have a graph that looks like this. This would be a concave up. That means the second derivative is positive. It's greater than 0. So that would be this situation and this situation. If I were to draw, and let's just make a few subintervals here. If I were to draw the midpoint approximation here, you'll see that not well drawn, but you would see that my rectangle is an underestimate, right? Now, if I look at a trapezoid would say, hey, find the endpoint y values, connect the dots. I'm sorry, that went a little bit too high. And then this would be the trapezoid. And it would say, okay, now use that one, and that would be the trapezoid. That would be an overestimate. That would be an overestimate. And so we're going to use the second derivative, which talks about concavity, to tell us whether or not it's an over or underestimate for midpoints and trapezoid approximations. And so as we go through this next exercise, just keep in mind this table. If it's a left and a right, we have to consider whether it's increasing or decreasing. Whether it's a midpoint or trapezoid, we consider whether it's concave up or concave down, the second derivative. But if they give you a graph, well, then you can kind of make a sketch and see what's going on. Like example number 4. The function f is a twice differentiable function with f prime being f prime of x being less than 0 and f double prime of x being greater than 0 on the interval from 2 to 7. Okay, so I'm going to go ahead and highlight that from 2. We're talking from here to here, as shown in the figure. Let L of S, R of S, T of S represent the left Riemann sum, the right Riemann sum, and the trapezoidal sum approximations for the integral between 0 and 7. Which of the following inequalities is true? So I need to compare L of S with R of S with T of S. Okay, so let's see. L of S would be the left-sided. Well, this is decreasing. We said when it's decreasing, my rectangles are going to be overestimates. R of S would be the right rectangles. The function is decreasing. That means this is going to be an underestimate. And so far, I have L of S has to be less than R of S. And now the question is, where does T of S come into play? Well, T of S is going to be from here to here. By the way, this is a concave up. So remember what we said, concave up. And they even tell me here, concave up means the second derivative is positive. Well, according to this, I should have overestimates, right? I should have overestimates. But when I draw it, even though this is an overestimate, this rectangle, is it as much as the overestimate of the left side? And the answer is no. The left side rectangle is definitely giving me more space than I need. Remember, we're looking for this shaded region. This would be the integral from 2 to 7. And the left-sided rectangle goes way above more than what I need. The trapezoid goes above, but a little bit more than what I need. And then the red one, the right-sided rectangle, gives me less than what I need. So in reality, I believe it should be, and then I need to compare it to the actual retail price. So let's take a look at this. Is the left less than the right? Well, no. We said the left, let me go back to the color that I use. We said the left side approximation was greater than the right side approximation, right? So this can't be true. I can eliminate that. Is the right side less than the left side? Yes. But is the left side less than the trapezoid? No. So this is off. The right side, is it less than the left approximation? Yes. Is that less than the actual retail price, the definite integral? Well, no, the definite integral is the exact, right? So it has to be between the lowest estimate and the highest estimate. It has to be in between. So no, this can't be right. Is the area under the curve in blue, the definite integral, less than the trapezoid? Yes, because we said the trapezoid approximation was an overestimate, which is less than the left-sided rectangle, Riemann rectangle estimate. Yes. So the actual retail price here is D. So using this table, or these tables, we can kind of get an idea of how to tell whether we're dealing, once we find the estimate of a Riemann rectangle or a trapezoidal approximation, we can tell whether that's going to be a value that's too much, an overestimate, or a value that's too low, an underestimate for our actual definite integral value that we're looking for. We'll come back and we'll do the next example, which looks very much like an AP free response question.